Okay, for the next few minutes here, real quick, we're going to go over a second example of using logistic regression. This is where we left off on the last video, and it's going to just focus on sunburn related to UV and temperature related exposures or risk factors at a beach. And moving forward, the amount of sunburn that was observed in this study of 947 participants who showed up at a beach without sunburn, 137 within a week later when they were surveyed by phone indicated that they in fact developed sunburn. So with the rule of tens, how many predictors would we be allowed to use? Probably about 13 or 14. That's a whole heck of a lot, so we probably wouldn't even want to do that. The simpler the model or the more parsimonious the model, the better. But we're going to just focus in on using a few predictors here. You can build these statistical models to have more variables, but you generally want to have only your most significant variables, or the ones that are p-values less than 0.05 in the model. So if you're trying to predict factors that put people at an increased risk for sunburn or having reported sunburn, these were a few that came out in this East Fork Beach study on these 939 swimmers that we had data on. So we see the odds ratio for the variable head in is 1.82. We see that the whole confidence interval is above 1, which makes that obviously statistically significant. The p-value is less than 0.05. UV, as UV goes up, the odds go up. That's entirely significant according to the confidence interval, and the p-value shows that. Temperature, as temperature goes up, again, the confidence interval for that odds ratio is entirely harmful, and that also is statistically significant. The whole model, the whole logistic regression model, is statistically significant. P is less than 0.0001 according to that value right there. So how do we interpret these? Well, these odds ratios, since there's multiple variables here, these are not crude odds ratios. Instead, we would call them adjusted odds ratios. And the adjusted odds ratio for a person putting their head in the water at the beach suggests that the odds for those people are 82% higher for them to have sunburn than those who did not put their head in the water. So the odds of sunburn among those who put their head in the water are 82% higher than the odds of sunburn for those who did not put their head in the water. With regards to UV, this is a continuous variable, so the best way to pronounce this or say this is the adjusted odds ratio for UV suggests that for each unit increase in the UV index, the odds of sunburn go up 61%. So a 1 unit increase in UV results in 61% more sunburn among beach users. For temperature, for each 1 degree temperature increase, the odds of sunburn goes up 10.3369%. The odds go up 10.3% for each 1 degree or 1 unit increase in temperature. Alright, so that's our model. Now remember, there were two things we wanted to look at. We wanted to look at model discrimination and model calibration. To look at model discrimination, we have that very simple, easy 4-letter command. Type in LROC and hit enter. And that will give us the area under the ROC curve that compares the sensitivity minus 1 minus the specificity. Remember, above 0.7 was acceptable, and 0.7 to 0.8 is kind of like fair. It's not really that great, but it's acceptable. So this model has acceptable discrimination in terms of its ability to properly classify people or predict people who had sunburn and properly predict people who did not have sunburn, dealing with maybe the specificity versus the sensitivity. So acceptable there. The next thing we would do is model calibration to make sure that the model has adequate fit, acceptable fit. So you can type in this command lfit, group, parentheses 10 table. Now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different groups that are expressed here Group 1, their probability of sunburn was very low. They said low risk, 0.0285 probability of sunburn. This group here was the high risk group. 35% of them were expected to have sunburn. And then here's how many people fit into each group. So we expected 16.6 in this group according to our model. We actually observed 20. In this model, or not in the same, in our model, we expected in this high risk group 32 not to have sunburn. We observed 29 to not have sunburn. This group, lowest risk group, we expected 98 people not to have sunburn. We observed 98 not to have sunburn. We expected 2 people. We expected 2 from our model to have sunburn. We expected 2. We observed 2. When we do the chi-square test on the observed versus expected in these different groups, it gives us a p-value of 0.0798. To some, that would be inadequate fit because it's still pretty low. But if you want to use your alpha cut point value of 0.05, you go ahead and do it. You can say that since this is greater than 0.05, there's no statistically significant difference between the observed and the expected. Some people would set that value at 0.2. This is very similar to the normality test, right? Where you want your data to be normal, and here you want a high p-value. You don't want your observed and expected to be different. You want good model calibration. You want this p-value to be high, just like a normality test. You don't want a statistically significant difference here. So the interpretation here is a little backwards from what other people would want to have on the other parts of statistics. But again, remember it. Low p-values mean statistically significant differences. Here we don't want to see a statistically significant difference. So we have acceptable fit by most folks' standards. Some people would set this bar a little higher and say you want a p-value of higher than 0.15. But for the purposes of this class, it's higher than 0.05, so you might say acceptable. Alright, so that concludes our 15 minutes and then some, an extra 7 minutes on a second example. So that finishes all of our notes for this class. So there's one more assignment and a review. I'll do a review recording for you, and that will conclude everything. Thank you. Bye.